So we have been looking at the approach of partial equilibrium approximation, and as a template set of equations or reactions, I'm sorry, we could let us look at about 3 forward and reverse reaction pairs leading up to a 4th reaction, which we deliberately take as a termolecular reaction so that it is slow. The idea being that if you now have these bimolecular reactions happening relatively faster and they are forward and reverse reaction pairs, then we can assume that because they are happening quite fast they could stay in equilibrium with each other, which means their respective forward and reverse reaction rates would match, and therefore the ratio of the rate constants of the forward and reverse reactions in each case would turn out to be the equilibrium constant based on pressure, right. And so we can write these equilibrium equations for each of those reactions, and therefore we now are rewriting these and numbering them as 1, 2, 3. So what's going on with this here is, here we are saying we recognize A2, B2 and A2B as stable species, and A, B and AB as intermediates, right. We are interested in d over dt of concentration of A2B, that is the final product whose rate of production we are interested in, right. Now looking at the 4th reaction where this is being produced, we could write this as concentration of A times concentration of, I'm sorry, equals Kf4 times concentration of A times concentration of AB times concentration of M, right. But we need to know what these are. The concentration of A and concentration of AB, which are intermediates, okay, in terms of concentrations of the stable species in the system, namely A2, B2 and A2B. If we were to suppose that we didn't have all these things, right, this is all too much detail. All I want to think about is A2 plus B2 gives you A2B, or maybe A2 plus half B2 gives A2B, right. I would like to write the rate equation as dc A2B divided by dt equal to k times, small k times concentration of A2 times concentration of B2 to the half. But there the powers that we are looking at, 1 and half, should really be orders and not molecularities, because that is like the global reaction, and we aren't sure that we can actually use the stoichiometric coefficients in the global reaction for the orders, right. That needs to be empirically found, and that is what we are trying to do with the detailed reaction. And here the detailed reactions tell us that this is actually in terms of the intermediates, which we don't want to deal with. We want to now express the concentrations of the intermediates in terms of the concentrations of the stable species. When we say stable species, we mean both reactants and products, because it is possible that the concentrations of these intermediates depend on the concentrations of products, stable products, as well as concentrations of stable reactants. So we shouldn't distinguish between products and reactants at the stable level. We should simply say stable species, right. So how do we find these is why we write out these 3 equilibrium equations, and you see what happens here. The intermediates are A, B and AB, and we have 3 equations. So we strictly speaking, if assuming that we are okay with dealing with A2, B2 and A2B, right, is it possible for us to write A, B and AB in terms of the stable concentrations? right, that is what we want to do. Having said that, we are interested only in these two, we are not really interested in concentration of B because that is not part of the final answer. So is it possible for us to eliminate concentration of B in these equations and look for only expressions for concentrations of A and AB in terms of A2, B2 and A2B is the rigmarole that we have to go through, yeah. So eliminating CB from equations 1 and 2, you can do this. So you can now write this with in terms of concentrations of A and B as if you are now looking at only A and B, do not worry about AB, let it be there, and then we have A and did I make a mistake?
Wouldn't that be the third equation reaction?
Which
there
one?
is also A to B in that.
I might have made a mistake, let me just check this.
There's A to B there. Product.
AB plus A2, yeah sure, yes.
So when I write dCAB by dt, I mean this step.
Okay. I understand what you mean. Yes, you're right. Okay, so you're right. So strictly speaking, what I need to do is to factor in. Okay, let's do that. Thanks. Plus K F3 is being produced in the forward reaction CAB CA2 minus K KB3 CA2B CA. Yeah, I was wondering about it myself because it is not so simple. It is not strictly speaking so simple. You could do this, but what you would find is this is equal to this because we are assuming equilibrium, alright, therefore it gets cancelled, right. So it is always good to go through the details, and yeah, therefore we are stuck with only this, right. If this were not to be cancelled, then we understand that this is unknown, but this is to be treated as known, and this is to be treated as a known, and this is unknown, and still we would be requiring concentration of AB and A to be expressed in terms of A2, B2 and A2B. This is the procedure that we are looking for. So if you now eliminate CB from equations 1 and 2, I'm sorry, here, yes, that's what I was searching for. Right. So yeah, so we now have this. So you can rearrange these things. Don't worry about AB showing up, which is an unknown, right, but you try to eliminate CB. What you get here is then CAB equal to KP1 KP2 CA2 CB2 the whole to the half. You can work out the mathematics, and you should be able to find that this is the case. Then using 3, right. So we have used 1 and 2 equations. Let's go to the third equation. We should be able to find there is a CA sitting there, and AB is something there, so we can plug this expression there, and so you can find CA equal to I am just giving the final answer, KP3 KP1 KP2 to the half CA2 to the 3 halves CB2 to the half divided by CA2B. Therefore, right, if you now write this equation as 4, right, that means we are primarily interested in this expression because those two terms got cancelled. So what happens is in 4 d c a to b divided by dt is equal to, you would have a kf 4 coming in, and therefore start with a small kf4, then you have everything else showing up, kp3, kp2, kp1, c_a2 squared, c_b2, cm that is still there. Well, just let me just write this in the same line, divided by c a to b. So that's the answer for you. I just worked it out for you, so you know you're not supposed, you should now know how to do these things, right? So look at what has happened. We now got an answer based on the stable species, which is a little bit more surprising than what you would have expected for a global reaction, alright, which is, first of all, it is going a square of A2. So you might argue, let me write the global reaction as, instead of A2 plus half B2 gives A2B, I might write this as twice A2 plus B2 gives twice A2B, alright, but then that would have meant that I need to have a 2 here, which I don't, okay. And then you would be able to say I can put a square here and a power 1 there, but the other 2 are extra, that you would have never figured out, right, unless you went through the details. And if you went through the details as it is without the partial equilibrium approximation, it would be a lot more horrendous when compared to having these algebraic equations replace your ODEs for the rates of the intermediates, right. So you now have a Cm, which is sort of like saying it depends on the container, what's the total number of moles that is there in the entire container, because as the pressure increases, this now goes as, the whole thing will now go as p square, p to the 3, because this is now going to have a contribution to the pressure, this is going to have a corresponding contribution to the pressure, and finally all the 4 of them should gang up and say it's going to go as p cubed, right. So this acts in bringing that up, on the one hand. Second, what is the A2B showing up in the denominator remind you of? Something that we went through last class, self-inhibiting reaction, right. The more A2B that you produce, the less the rate at which you are producing it, is what this really means, and that is because A2B is actually participating in the reverse reaction as well. So more it's getting produced, it's also getting depleted, alright. So all these things kind of come up in these expressions based on the approximations that we do. So let me also give you a simple example which is a little bit more realistic here. So example, just like how we had the what should I say, the hydrogen bromide example for the steady state approximation, here let us suppose that we have H2 plus O2 gives and takes with K1 here, K2 for the reverse, 2H OH on the other hand, and H2 plus OH gives K3 H2O plus H, okay. So here we find that d over dt of CH2O equal to K3 CH2 COH, and I don't like COH sitting there in this. I would like to actually have H2 is already there. I would like to express COH in terms of H2O2 and maybe H2O, that's permissible, right, that's what I want to do. So I use the equilibrium approximation I use the equilibrium approximation and say Kp Kp2 I should Kp1 let me use the notation Kp1 comma 2 are equal to COH squared divided by CH2 CO2, right, alright, that is equal to K1 divided by K2, alright. Now keep in mind when you write Kp, strictly speaking we should be writing POH squared divided by PH2 PO2, okay. It just turns out that the molecularity is the same for both the forward and the reverse reaction, and therefore the total pressure gets cancelled out and you can write in terms of concentrations directly. If the molecularities are not the same for both the sides, then you will get into trouble. So a more direct thing to do is to probably write Kc instead of Kp, but if you are insisting on Kp, then there is a conversion between Kp and Kc that we have gone through that you need to factor in, yeah. So if you now use this, then what happens is from here you try to evaluate what your COH is. So COH then is Kp1 comma 2 CH2 CO2 all to the half is what we have, and therefore the CH2O is K3. Let's now get rid of Kp12, use K1 and K2 because they are like given information in the reaction scheme, and you can say this is K1 divided by K2 to the half, CH2 to the half goes with CH2 there, and so it's like CH2 to the 3 halves and CO2 to the half remains. So you have CO2 to the half, right. So that's the final answer. What it means is if you were having this as the reaction scheme, like a 3-step reaction scheme for production of water, right, then the partial equilibrium approximation tells you that this is partial equilibrium. Tells you that the rate of production of water actually depends to 3/2 the power of CH2 and 1/2 to the power of O2, okay. These are now the orders with respect to H2 and O2 respectively. Together if you now look at the total order, right, 3/2 plus 1/2 is 2, so you can easily see that this is like a second order reaction that we are looking at, alright, but the division between the fuel and the oxidizer is not equal. That's a lesson that we learned from these things. Alright, let's now do some chemical explosions based on what we have learned, okay. So this is the last topic that we would like to cover under chemical kinetics before we proceed on further with other things in combustion. So let's consider the following schematic reaction mechanism. Right. 1, X gives you R with reaction rate constant K1, 2, R gives you alpha R with a rate constant K2, 3, R gives you K3 P plus R, 4, R goes to S and 5 R okay 5 goes to X. Now this is obviously looking a bit strange. If it isn't looking strange, then you must be a genius, right? What we mean by a schematic reaction mechanism here is this reaction scheme is focusing only on the intermediates. That means there are hidden stuff around that are stable on either side, which we are not worried about. Okay, why so? Because you can now clearly see that this is a chain initiation step, right? Because this is the birth of an intermediate. R is the intermediate that we are looking at. R becoming alpha R for alpha greater than 1 means we are now branching more and more. Okay, so this is like some intermediate giving rise to more intermediate, right? So this is chain branching. Of course, alpha less than 1 would mean chain termination kind of reactions, right? But they don't really show up like high up in the list. Okay, they are kind of the end. And R gives P plus R. P is like a stable product. Like let's say we are interested in this finally. Okay, but then what's happening? You start with R, you have something else, and then you also have R. So as far as intermediates is concerned, it's neutral. That means it's a chain propagation. Yeah, so you have a chain propagation step. In reality, you would have a bunch of steps like this. Okay, so each of these kinds of things could be like a bunch. It's not just one. Okay, R going to S is schematically representing chain termination at a surface, whereas R going to X means chain termination at in the gas phase. In the gas phase, X is any molecule, right? So you could have started with any X giving rise to intermediates, and R could go back to any X. Okay, so in that sense, this is not strictly like a reverse of that, because this X could be anything. Yeah, but we are making a distinction on the way the intermediates are getting terminated, either at the surface around anywhere or in the gas phase by colliding with other molecules around and disappearing, okay, and becoming some stable species. So note that we make a distinction between termination at the surface at a surface, it does at a surface, and termination in the gas phase. Why would you want to make the distinction? How does it matter? Okay, termination means the intermediates disappear, right? How does it matter which way they disappear? What are we looking at? So whenever we were doing things in the past, I asked you to keep an eye out on distinctions between unimolecular reactions to bimolecular reactions in a scheme, or bimolecular to termolecular reactions in a scheme and so on, and the reason was to look at the pressure dependence of the rates of these reactions, okay, or the differences in the pressure dependence of the rates of these reactions. And so as you change the pressure from low pressure to intermediate pressure to high pressure, the importance of these different reactions becomes different, right. So effectively we were looking at what's it going to be in terms of pressure. Similarly, looking at the termination either at a surface or in the gas phase is going to be dependent upon pressure, because a surface termination is relatively independent of pressure. A surface is a hard surface, it's not going to change its packing depending upon the pressure, okay, whereas a gas phase is going to actually get more and more packed, okay, with less and less mean free paths for the collision between the molecules as you increase the pressure. So what you would expect is, as you increase the pressure, the termination via the gas phase is going to be more and more predominant when compared to the termination via the surface, okay. So this distinction is going to enable us to tell us how things are going to change with pressure, right, and that's the reason why we want to make this distinction. So there's another way of distinguishing things as far as particularly intermediates is concerned, okay. So the termolecular, bimolecular and so on is for any species, it does not have to be intermediates, but here we are specifically talking about termination for intermediates in two different parts, and they are dependent on pressure in different ways, okay. That is what we want to try to explore, okay. So then let us look at how to write the reaction rates for these. Now I am going to write these things in such a way that we care only about concentrations of the intermediates, we will not worry about concentrations of stable species, okay. They are not showing up in the schematic reaction mechanism anyway, okay. There are stable species around which we are not simply bothered about, because when we looked at a reaction mechanism before, to characterize it as a chain initiation, branching or propagation or termination, we were primarily looking only at the intermediates, okay. We just disregarded the presence of the stable species, okay. We are always looking for our intermediates being created, more of them created than what's being consumed, or the same amount is created, and we didn't even distinguish between the intermediates, like it could be OH on one side and H on the other side, doesn't matter, they are all very active radicals anyway, right. So they are going to kind of propagate the reactions if one of them got killed and the other one got produced, right. So this is the way we were looking at it, and obviously they were reacting with stable things like H2 or O2 and so on, which we didn't really worry about, and these are all there. So since they are hidden, we can't write rate equations exactly depending upon their concentrations. So we are going to write equations that are sort of functionally correct but not accurate, right. So that's what we will end up doing. So let us say the first equation, so the rate equations for these are, one, let us say we call this omega I for the chain initiation step, all we are going to write is dCr over dt, because we do not want to be worrying about the fact that it depends on the concentration of X, okay. We could write K1Cx for example, okay. Let me not worry about it, okay. I am just going to keep this as omega I, right. Second, omega, let us now call this chain branching, so we will call this omega B, that is equal to dCr over dt as well. For this reaction here, this would be written as K2, strictly speaking I should write alpha minus 1 K2 Cr times other things which are hidden, right. So since I do not know what those are, I am simply going to write this as equal to Fb times alpha minus 1 Cr, alpha is a parameter here, FB is like it's going to take care of K2 dot 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 is like concentrations of stable species, okay, which doesn't enter the picture. So essentially what you're saying is let's deal with F's rather than K's, because the F will couch things that are not really important. What we want to explicitly keep is CR, okay, and so this is a production step. So we will call this as omega p. The third step, this is dCp over dt. This is equal to FPCR, okay. Here the intermediates are neither getting produced nor consumed on the whole, but so you could say that this is basically Fp is of the order of the same as K3. You don't, but you could have something hidden, right? So we just write F instead of K, and for let's call the surface termination reaction rate. So we have a negative dCr over dt there, and that is FSCR. We do not know what else is there other than R on the left hand side, so we just write Fs instead of K4, and similarly let's call this omega g for gas phase termination reaction rate. This is again minus dCr over dt equal to FGCR, alright, okay. So we have explained what the F's are there, and I also told you what why this is a schematic here. So the rate of production of the intermediates, then the net rate of production of intermediates dCr over dt from all the reactions equal to omega I plus Fb times alpha minus 1 Cr minus Fscr minus Fgcr. The third reaction did not have a net rate of production of intermediates at all, okay, because it's a propagation reaction. Yeah. Therefore, we have only 4 reactions that are contributing here. 2 of them where things are produced if alpha is greater than 1, that is. If alpha is less than 1, this would mean consumption anyway, and obviously here the radicals are getting consumed. Yeah, and keep noting that these things depend on concentration of Cr, because it's like chain branching or termination, but omega I does not depend on concentration of Cr because it's starting from things that are pre-existing, that is, they are not intermediates. Fine. We now apply the steady state approximation, right. Or if you want to be quite precise, we should say quasi steady state approximation. That means dCr over dt, the net rate of production is approximately equal to 0 for bulk of the time when reactions are proceeding, right. So this implies we now say that omega I plus Fb alpha minus 1 Cr minus Fs Cr minus Fg Cr is approximately equal to 0, from which we can try to find out the concentration of the intermediate. So this implies Cr is equal to omega I divided by Fb alpha minus 1 minus Fs plus Fg. okay. So the steady state approximation did this for us. You go back and think about what we did. What it means is we want to get algebraic equations that govern the concentrations of intermediates, right, so that we can evaluate the concentrations of the intermediates in terms of the concentrations of the stable species, and then plug those expressions in the rate equation for the production of products. That is what we are finally interested in, right. So what we should then say, then we are interested in dCp by dt, that is the products. It is kind of like this kind of like life, you know, we should be interested in the in producing products, but we keep going talking about intermediates, like in most of our lives that we just get caught up in intermediates, right. So let us not lose sight of our goal. Our goal is actually dCp over dt, right, Fp times Cr. Of course in life money is one of the biggest intermediates that distracts us, right. Yeah, where I'm losing now. Cr or here, because let's admit that by swapping the denominator. I don't like negative signs for concentrations, right. So we say Fs plus Fg minus Fb times alpha minus 1. Happy? You need to keep me happy as well. Don't get negative concentrations, right. Your advisors are not going to like you when you get them, right. So so you want to have a positive quantity there. Okay, so Fpcr then is Fp omega I divided by Fs plus Fg minus Fb times alpha minus 1. Okay, I pointed out this for you earlier in the context of, let us say, the HBr reaction or example, or I do not remember what, but let me do this once again, and this becomes very intuitive for us. What is happening in this expression for you is these are, this is a this division, sorry, I'm sorry, this difference here is basically telling you the competition between termination and production, okay, which is being compared with omega I, that is the initiation, okay. Or in other words, the rate of production of your final products depends on what is the interplay between the rate of production and rate of consumption of the intermediates for a given rate of initiation of the intermediates. Once you have intermediates initiated and left into the pool, then the dynamics of how they are produced further by chain propagation, branching steps versus chain termination steps, okay, that ratio is what determines your rate of production of products, you see. So it is sort of like telling us the entire physics of what is going on, right, just the expression, looking at the expression. Fine, if you did not worry about all that stuff and you now said this is the expression, when you look at it, what would you worry about? Again, I am trying to kind of ingrain certain traits in you. You now look at an expression, and the moment you have a square root there, you should be worried about whether the stuff inside the square root is going to become negative, right. So similarly, when you see a logarithmic expression, you have to look at whether the argument is going to actually become negative or 0 and so on. So these are all like things that got to be wired in your head. Similarly, and these are like the square roots and logarithms don't happen all the time, but ratios do happen many times, right? And the moment you see a ratio and you see the denominator, you have to start looking at, oh my god, is this denominator going to become 0, right? We are always afraid of infinity, okay? So we have to start looking at when would this denominator ever become 0, yeah. So for alpha less than 1, the denominator is always positive, right? And what is meant by alpha less than 1? When you now have alpha less than 1, I first of all told you that this reaction shouldn't belong in that place there. It should be somewhere below, because it's beginning to actually annihilate itself. The intermediates are actually consuming themselves, right? But that's not what we are talking about for the reactions being up there. We are now talking about the alpha typically greater than 1. That's what chain branching is all about, right? So when you now have alpha greater than 1, okay, for alpha greater than 1, then you have a positive quantity here and a positive quantity there, and it's possible that they become equal. Oh ho, we have a problem, right? So Fs plus Fg equal to Fb times alpha minus 1 implies denominator goes to 0 and dCp over dt goes to infinity, right? This is what we are talking about as chemical explosion. It is basically saying that once you have produced your intermediates, okay, at whatever finite non-zero rate, so long as the intermediates are producing themselves more and more and consuming themselves at the surface or in the gas phase in such a way that the rate of their production matches the rate of the consumption, right? You are now going to be continuing to produce products like crazy. The rate of production of products is just going to go on and on, very high. So that means you are going to produce a lot of products. So the intermediates are actually playing a sustained role in a continuous production of products at a very infinite level, infinite rate, right? So this is essentially the basis of chemical explosion. And then what you're going to do is to say, well, let me begin to distinguish between Fs and Fg as we change the pressure, okay? So at low pressure we now expect that Fs should predominate over Fg, and at high pressure we expect that Fg should predominate over Fs, alright. So this is what we are going to be doing. As P increases, Fs decreases relatively, right? But Fg is not too large, right? For low P, because you don't have a vigorous gas phase termination at low pressure. That is, together Fs plus Fg decreases as P increases, okay. So you now have a limit, you now reach a limit, okay. So we reach a limit, that means we are looking for, as you change the pressure, how is this going to change relative to this, such that at some limit you might equate, right. So we reach a limit where the radical generation just exceeds the termination right. So let us suppose that we started out with a very, very low pressure, alright, and we now found that from there, as you increase the P, okay, the termination actually comes down and in this low pressure range, because Fg is not very active yet, because the pressure doesn't increased a lot, but Fg is something very, very small at this pressure. So you are now actually having a situation where the termination is coming down but the generation is going up, and therefore you now reach a point where the generation just exceeds the termination, and the moment when you say just, that means this is just beginning to equal that. So far this was higher, this was lower, this is now increased, so it is getting to this, and therefore you now have an explosion limit, okay, for starting, so let us say termination starting from some low P for a given T. Okay, you fix the other thermodynamic variable and you get this. So this is what you would call as a first explosion limit, okay. And then as you now look at this dynamics, we do not care which is higher, which is lower, all we are looking for is when things match, alright. So when this keeps on going, as you change your pressure, if this catches up again, then you again have an equality, which is bad, right. So as pressure increases further, right, Fg increases, okay, which implies Fs plus Fg increases, okay, and here the termination catches up with the generation, right. Then this is what will lead to the second explosion limit, alright. We will stop here and pick up from here in the next class.